Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So in this question, we're told that a person has a mass of 75 kilograms and they take off on snow across using jet-powered skis. And the skis have a thrust of 200 newtons. There's a coefficient of friction between the skis and the snow of 0.1. And the skis run out of fuel after 10 seconds. We're asked to calculate what Sam's top speed is and how far he travels when he finally comes to a stop. So in order to tackle part A, what is Sam's top speed, we're going to need to know what that acceleration was in the first part of the motion where the skis are actually working. So when the skis are working, we've got a free body diagram that looks something like this, where we've got the thrust force from the skis propelling the object forward, and then we have a friction force pulling back on the system as well. So in order to find acceleration, we first need to do a calculation of F net. And so that will be the thrust force subtract the friction force. And the thrust force was given to us, so we can fill that in a moment. But what is the friction force? So usually that's calculated as mu Fn. Since the skis and the person are on level snow, and the normal force and the gravitational force are the only forces acting in the y direction, we know that the normal force here will be equal to the gravitational force. So we can, instead of writing Fn here, we can just go ahead and substitute mg. So the thrust force is 200 newtons. The coefficient of friction was given to us as 0.1. The mass is 75, and the acceleration due to gravity, 9.81. So once we plug that into our calculator, we get a final value for F net here of 126.4 newtons. We can then use that to calculate the acceleration. Acceleration will be F net divided by m, so the 126 divided by 75, and we get an acceleration, keeping a few decimal places, 1.686 meters per second squared. So that's our acceleration, and then we can use that combined with the other variables given to find the top speed. So what are we trying to find here? We're trying to find the final speed. We can assume that the initial speed was 0. The acceleration, which we've just calculated, is 1.686, and the time was given to us as 10 seconds. So the final speed, or the top speed, the final speed while the skis are on, is going to be given by this formula here. And we can just cancel out that first term on the right-hand side because that's 0. And if we want to, oh, you know what a better formula to use would be? Sorry, because we don't have displacement. A better formula would be A delta V over delta T. So we can just calculate the change in speed as A delta T, which would be the 1.686 times 10 seconds. So we get a change in speed of 16.86 meters per second. But of course, the initial speed was 0, so that's just the final speed, right? The final speed is 16.86 meters per second. So that is our answer, our final answer to part A. In part B, we have to calculate how far Sam traveled when he finally comes to a stop. So there's two parts of the motion, one where the jet skis are working and one where they're not, right? So let's calculate those two displacements separately. So let's start working with the first part of the motion. So we can use this formula here to calculate the displacement while the skis are working. I'm just going to call this D1. And this formula is good because we can ignore the first term. That'll just be 0. And let's see. So our acceleration was 1.686. Our time was 10. And so we can calculate the distance as 84 meters. And then we also need to calculate the displacement after the jet skis have stopped working. We need to calculate a displacement for that part of the motion as well. But the acceleration is going to be different, right? Because if the jet skis stop working, there's no longer a thrust force. So the net force here will be equal to just the friction force. So the friction force we know is mu k mg. We've already discussed that. And so if you plug in the values here, you're going to get a value of 73.6 newtons for the friction force. And so the acceleration we can find by dividing this net force by mass. And so the acceleration will be negative 0.98 meters per second squared. And then we can do our final calculation where we use kinematics to find the distance traveled during this time. So how are we going to find that? We can use this formula. Oops. And just rearrange for D. The final speed is going to be 0 because we're coasting to a stop. The initial speed is going to be the speed that we found previously, because the initial speed for the second part of the motion is the final speed from the first part. So I'm going to pull the VI squared to the other side and divide everything by 2a. So that'll give a formula negative VI squared over 2a. And then I'm going to plug in all my values. And so we get a displacement, let's call this D2, for the second part of the motion. We get a displacement of 145 meters. And so overall, the total displacement for this object is 84 meters plus 145 meters, and that gives a total of 229. So this is how far the person has traveled when they finally come to a stop, taking into account both parts of the motion. This is the final answer for part.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
We know that angle of inclination is theta is equals to 20 degree. Height of the inclination is small h is equals to 2.0 meter. The coefficient of friction between the bike tire and the inclination surface is mu is equals to 0.02. Width of the pool small d is equals to 10.0 meter. Acceleration due to gravity small g is equals to 9.81 meter per second square, and the initial speed of the bike vi is equals to 111.0 meter per second. We have to calculate the distance of landing position from the end of the inclination. Now consider mass of the motorbike is small m. Hence the weight of the system is W is equals to mg. Now the weight will act vertically downward. So the component of the weight along the inclination is Wi is equals to mg sine of theta. Now the normal reaction of the surface of inclination is capital N is equals to mg cos of theta. Hence the frictional force F is equals to mu of mg cos of theta. Hence the total force acting on the motorbike is capital F is equals to mg sine of theta plus mu mg cos of theta. So the acceleration of the bike is acceleration A is equals to force upon m is equals to g sine of theta plus mu g cos of theta. Substituting the values, we have A is equals to 9.81 meter per second square multiply sine of 20 degree plus 0.02 into 9.81 meter per second square cos 20 degree. And hence after solving this we get the value of A is 3.54 meter per second square. Now the total distance travelled by the motorbike is distance is equals to h upon sine of theta, which is equals to 20 meter divided by sine of 20 degree. Hence we get 5.85 meter. Hence the final velocity of the bike while leaving the ramp is V final is equals to V initial square minus 2as, which is equals to under root of 11 meter per second square minus 2 into 3.54 meter per second square multiply 5.85 meter. Hence we get 8.92 meter per second. So the bike leaves the ramp it with speed V final is equals to 8.92 meter per second at an angle theta is equals to 20 degree from the height small h is equals to 2.00 m. We have to calculate the horizontal range. The horizontal range of the projectile is given by d is equals to vf square upon 2g. 1 plus under root of 1 plus 2gh divided by vf square sine square theta into sine 2 theta. Now substituting the values, we have small d is equals to 8.92 meter per second square divided by 2 into 9.81 meter per second square. Hence 1 plus 1 under root of 2 into 9.81 meter per second square 2.00 meter divided by 8.92 meter per second into sine square of 20 degree into my sine of 2 into 20 degree. We get 8.56 meter. Conclusion.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
For this problem on the topic of dynamics, we're told that a 5,000 kilogram interceptor rocket is launched at a given angle, and we are given the thrust of the rocket motor as well. We want to find an equation that describes the rocket's trajectory. We want to know the shape of this trajectory as well as the elevation at which the rocket will reach the speed of sound. Now we'll use the particle model and the constant acceleration equations of kinematics for the rocket. the acceleration of the rocket in the launch direction is obtained from Newton's second law, which says that the resultant force acting on the rocket F must equal to its mass m times its acceleration a. Now we know the force acting on the rocket is given to be 140,700 newtons. And we also know the mass of the rocket, which is 5,000 kg. So that's 5,000 kg times the acceleration a, which means that from here we can find the acceleration a to be 28.14 meters per square second. Now we need to find an equation that can describe the rocket's trajectory, so y is a function of x. So we need to find the x and y components of this acceleration. So the x component ax is the magnitude a times the cosine of the launch angle 44.7 degrees. And this gives us the x component of the acceleration to be 20 meters per square second. The y component of the acceleration, ay, is the magnitude a times the sine of 44.7 degrees. And calculating, this is 19.8 meters per square second. Now the net acceleration in the y direction, therefore, is follows. Remember, there is a gravitational acceleration acting vertically downwards on the rocket at all times. So a net in the y direction is equal to the acceleration ay minus the acceleration due to gravity g. So this is 19.8 minus 9.8 meters per square second, which gives us the net acceleration in the vertical direction to be 10 meters per square second vertically upward. Now, with this acceleration, we can write the equations for the x and y motions of the rocket. So the y motion, y is equal to the initial position y naught plus the initial velocity in the y direction v naught y into t minus t naught plus a half times the net acceleration in the y direction into t minus t naught all squared. And so this is equal to 0 for the initial y position of the rocket plus the initial y component of the velocity, which is also 0, plus a half into the net acceleration in the y direction, 10 meters per square second, multiplied by t squared. And this obviously simplifies into a half times 10, which is 5 meters per square second times t squared. Now we can do the same for the x position of the particle. So x is equal to x naught plus v naught x into t minus t naught plus a half a net. So the net acceleration along the x direction times t minus t naught all squared, which is equal to, again, 0, since the initial position of the rocket is at 0, plus 0 for its initial velocity, plus a half times its horizontal acceleration, which is 20 meters per square second times t squared. Again, we can simplify this to become a half times 20, which is 10 meters per square second times t squared. So now we can relate x and y as follows. if we take x over y, we get this to be 10 meters per square second times t squared over y, which is 5 meters per square second times t squared. So this simplifies to simply 2, which means that we can have an expression of y in terms of x. So the position of the particle y of x is simply equal to a half x. Now for the next part of the question, for part B, we want to use this equation and find the shape of this trajectory. Well, we can see that this is in the form of a straight line. So the shape of this trajectory on a xy axis will be a straight line with slope half. Now, finally, we want to know the elevation at which the rocket reaches the speed of sound. Now, in general, we have Vy is equal to V naught y plus the net acceleration in the y direction times the change in time t1 minus t naught. And we know this to be 0, since the initial velocity of the rocket is 0, plus 10 meters per square second times t1, since t naught is equal to 0. Similarly, for the x velocity, vx is equal to v naught x plus the net acceleration along the x direction, again into t1 minus t naught, which also simplifies to 0 plus 20 meters per square second times t1. So the time required to reach the speed of sound will be calculated as follows. So 330 meters per second, the speed of sound, is equal to 22.36 meters per square second times t1. And so we can find t1, and we get t1 to be 14.76 seconds. Now that we have the time, we can find the elevation of the rocket using the y equation. So y, we know, is 5 meters per square second times t1 squared. So substituting t1 to this equation, we get this to be 5 meters per square second multiplied by the time, 14.76 seconds, all squared. This gives us the elevation of the rocket when it reaches the speed of sound to be 1,090 meters.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
In this problem, we're going to talk about Newton's second law. So what we need to know is that the total force applied on an object is equal to its mass times the acceleration. Okay, So in our problem, we have a rocket that is attached to a puck. So the puck is here and the rocket is just on it. And the rocket is headed towards the edge of a cliff that has a height of 2 meters, and the length of the table is 4 meters. Okay, so the end of the table is 4 meters from the start position, and then there is the table is located 2 meters up from the ground. And the thrust, I'm going to call it T. This is the force that is exerted over the rocket, is equal to 2 newtons. The mass of the system is 1 kilogram, and our goal is to find how far from the table the puck lands in a horizontal direction. Okay, so how far from the base of the table the puck lands. Okay, so first notice that the acceleration is equal to the force, which in this case is T divided by the mass m, and that is 2 meters per second squared. This is the acceleration of the system on the table. When the system, when the object reaches the edge of the table, its velocity v will be equal to, according to Torricelli's formula, the square root of 2a times delta x, where delta x is 4 meters. So this is the square root of 2 times the acceleration of 2 meters per second squared times delta x, which is 4 meters. And this is 16 meters per second. I'm sorry, 4 meters per second. This is the speed. I'm even going to call it v0. This is the speed when the system rocket plus puck reaches the edge of the table, and then it starts to fall. Notice that in the y direction, the only force is the gravitational force, so the acceleration is the gravitational acceleration. The acceleration in the y direction, which is 9.8 meters per second squared. So y, the y coordinate, is equal to g times t squared over 2. So the time it takes for the puck to reach the ground is the square root of 2y over g. So this is the square root of 2 times y, that's 2 meters over g, which is 9.8 meters per second squared. And this is 0.64 seconds. Now let's see how much this corresponds in the horizontal direction. So x is equal to v0x times t plus the acceleration in the x direction times t squared over 2. v0x is 4 meters per second. T is 0.64 seconds. The acceleration, as we found before, is 2 meters per second squared times 0.64 seconds squared divided by 2. So x is equal to 2.96 meters, which concludes our exercise.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
The thrust and the initial velocity both are in horizontal direction. Hence, they don't have any component along the vertical direction. So the time taken by the rocket to fall on the ground is small t is equals to under root 2h upon g. Now we can put the value of h here, under root 2 into height 40 meter divided by gravitational constant 9.8 into meter per second square. Now we get it is 2.85 seconds. Now the horizontal acceleration of the rocket is, this is part A. Now the horizontal acceleration is small a is equals to ft upon m is equals to 20 Newton divided by 0.5 kg, which is equals to 40 meter per second square. Hence, the horizontal distance traveled by the rocket is d is equals to v1t plus half at square. Now v 0.5 meter per second, t 2.85 seconds plus half acceleration 40 meter per second square into 2.85 times seconds square. Now we get distance 164 meter. Conclusion: the rocket will land 164 meter away from the base of the wall. Part B. The x position of the rocket at any time t is given by x is equals to VIX into t plus half AXT square is equals to 0.5 meter per second into t plus half of 40 meter per second square into t square. Since 0.5 meter per second t is less than 1 by 240 meter per second square t square, we can ignore the first term and write that x is equals to 20 meter per second square into t square. Solving for t square, we have t square is equals to x upon 20 meter per second square. And the y position of the rocket at the same time t is given by small y is equals to y naught, which is y naught minus 1 by 2 ay t square. It is equals to 40 meter minus 1 by 2 9.8 meter per second square t square. Now substituting t from equation, here we have equation number 3, this is equation number 2, and this is equation number 1. Substituting the equation from equation 2 to equation 3, we have y is 40 meter minus half 9.8 meter per second square into x upon 20 meter per second square. Y is equals to 40 meter minus 0.245x. Conclusion: the above equation is an equation of line, hence the trajectory is a straight line.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Given a geosynchronous orbit in which there is less satellite, the height of the orbit is h is equals to 3.58 into 10 raised to power 7 meter. To determine the time period of the time period of satellite is 24 hours. Because the orbit in which it is rotating is geosynchronous, that means the period of satellite is same as the time taken by Earth for one rotation. then only it is possible for all the satellites to be seen as a fixed from Earth, otherwise we would have observed it moving instead of fixed at one point. Part B. To find the value of g at height, small is t is equals to, we have the formula 2 pi under root r upon g, which is equals to t square is equals to 4 pi square r upon g. Hence, small g is equals to 4 pi square of r upon t square. Here we have t is equals to 24 hours. Hence, we can put 24 into 60 is equals to 86400 seconds. Here, small r is equals to h plus re. We have 3.58 multiplied 10 raised to power 7 plus 0.6371 into 10 raised to power 7, which is equals to 4.217 into 10 raised to power 7 meter. Hence, small g is equals to 4 pi square into 4.217 into 10 raised to power 7 divided by 86400 square. We get the value of small g 0.223 meter per second square. C. To determine the weight of the satellite in given orbit, mass of the satellite, here small m, is equals to 2000 kilogram. W is equals to m into g, which is equals to 2000 multiply 0.223, which is equals to 446 Newton.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
The axis of rotation of Earth possesses there is a pole of Earth, hence there is no centrifugal force acting on the pole, whereas the centrifugal force is maximum at the equator. Maximum at equator centrifugal force. Since the centrifugal force acting vertically outward, the centrifugal force will oppose the weight. Hence the weight will be higher at pole compared to equator. The rotational speed of Earth is omega is equals to 2 pi upon 86400 seconds. Hence we get 7.27 into 10 raised to power 5 radian per second. Hence the centrifugal acceleration is AR is equals to omega square R, hence which is equals to 7.27 into 10 raised to power 5 radian per second square multiply 6.637 into 10 raised to power 6 meter. After multiplying them we get 3.37 into 10 raised to power minus 2 meter per second square. Now the weight of the pole will be Wp, which is equals to mg, and the equator will be We is equals to mg minus m omega square r, which is equals to m of g minus omega square r. Hence the difference in weight is delta W is equals to, we have Wp minus We, mg minus m, g minus omega square r. Hence we get the value, it is m omega square r. Now substituting the value, we have delta W is equals to 75 kg multiply with 3.37 into 10 to the power minus 2 meter per second square. We get it is equals to 2.5 Newton. Conclusion: the reading of weight machine will be higher at pole. The reading will be higher by 2.5 Newton.
Homework pressure? No more. At String Library, we explain every topic in simple way. Join the learning family and score high every day.
It is given that small m is equals to 20 plus 5, 25 kg. Theta is equals to 20 degree. Small r is equals to 2.0 meter. Now theta, here we have t cos of theta, sin theta, tension T, mg, downwards. Here given small m is equals to 25 kg, theta is equals to 20 degree, radius is equals to 2.0 meter, omega is equals to 14 rotation per minute. Hence we can convert it 1.41 rotation. T sine of theta is equals to mv square upon r. T cos of theta is equals to mg. Now T minus mg cos of theta is equals to mv square upon r. Now T minus mg cos of theta is equals to mv square upon r. Hence T is equals to mv square upon r plus mg cos of theta. Hence T is equals to mr square omega square upon r plus mg cos of theta, because we know that V is equals to r omega. Now we can write it as, we can cancel r with r, we get m r omega square plus mg cos of theta. Hence we can take common m and we get r omega square plus g cos of theta. Hence after putting the values of m 25, r2 into 1.41 square omega plus 9.8 cos 20 degree, we get 25 multiply 3.9762 plus 9.8 multiply 0.9396. We get 25 multiply with 3.9762 plus 9.2089. Answer is 25 multiply 13.1851. We get 329.6, nearly equals to 340 Newton.
Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Hi. In the given problem, mass of the ball is given as m is equal to 500 gram, or we can say this is 0.5 kilogram. Length of the string is L is equal to 1.5 meter. It is given that the tension in the string at the bottom of the vertical circular track and that tension is given as TA is equal to 15 Newton. If we consider this to be the circular track, the vertical circle, then when the ball is at the bottommost point, its weight mg will be acting vertically downward. This point is supposed to be A. This is center of the circular path. This will be tension TA in the string in vertically upward direction. So, using free body diagram of the ball, the net force acting on this ball will be TA minus mg, and that will serve as the necessary centripetal force, which is given as mv square by r. For r, here this is L, means length of the string. So, the expression for TA here will come out to be mg plus mva square by L, or we can say this is m into g plus va square by L, or we can say g plus va square by L is equal to T by M, or this va square by L is equal to TA by M minus G. Plugging in the known values for tension, this is 150 divided by mass 0.5 kilogram minus 9.8. So it becomes 30 minus 9.8, which comes out to be 20.2. So VA square becomes 20.2 into L, length of the string. So this VA comes out to be square root of 20.2 multiplied by length of the string, which was given as 1.5 meter. So it becomes square root of 30.3 meter per second. Or finally, the speed of the ball at the lowermost point, at the bottommost point, comes out to be 5.5 meter per second. And here it becomes the answer for the given problem. Thank you.